Now that we have talked about the concept of threads in operating systems, and we have briefly discussed how different operating systems internally handle threads, as in the operating system itself being threaded in some way, let's talk a bit more about thread scheduling. And threads basically provide an abstraction of infinite resources to a thread, to the program running on a thread. And that is basically by having the operating system scheduling the threads in such a way that will enable some sort of fair usage of resources among the different threads on these running on the system. And it is quite important that every single thread running on your computer gets some time on the resources. Otherwise, the thread will be idle and will basically never have the feeling of making any progress. Some threads will be faster. So, for example, if your thread doesn't involve any I/O operations, then well, you're just touching upon the CPU, and the CPU is pretty damn fast. Also, the memory is kind of fast. It's slower than the CPU, but it's much faster than, for example, you typing on a keyboard or the hard disk. So some threads will, in general, be much faster when it comes to how they run. And one very important thing to note is that your program should be designed such that you never make an assumption on when and how your thread will be scheduled. So you cannot make an assumption, for example, on which thread will get scheduled before which thread. These kinds of things. And this is very important when you're doing concurrent programming, because you want to make sure that your threads run in the correct way. And you want to take into account that some of the other threads will run much faster than the threads that you have, while some others will be much slower. And this figure basically shows the thread execution model, which is basically the thread thinking that it runs on a dedicated virtual resource or a dedicated virtual processor. But that virtual processor is just of unpredictable and variable speed. So to each thread, it feels like it has its own processor, just running with at different speeds, at stopping and idling and so on. And processors are in general not your bottleneck because they are pretty fast. If your program is correct, then you should be able to implement your program such that you get enough. Your processor is not a bottleneck. So let us ask a question. I want you guys to reason about the execution of the threads in here. So there are 3 threads, and when do you think that this is possible? When do you think that this execution model is possible? And when do you think that this execution model is possible? Do you think that it's hardware dependent, or do you think that it has to do with the operating system? So let's talk a bit more about the problems that you may foresee already when in the threaded programming model. You have to have preemptive multitasking. So you need to basically be able to preemptively remove some threads from using the resources because, well, they have been running for too long, or because they're blocked on for some reason, or even because they are just doing things that they are not supposed to do. And you might need to do that while having 4 cores and all 4 of them running 4 different threads. So you have preemptive multitasking. As we said, you should never make assumptions on the speed of your thread, and you should always not also make assumptions about if 2 threads share memory or some resource on who writes first or reads first, unless you explicitly implement this in your program. And we will talk quite a bit about synchronization, about things such as locks and semaphores and so on in the operating system and in concurrent programming. Thread operations they usually have very simple interfaces. Well, thread create, which creates a new thread to run some function. So you basically, this calls a function to create a new thread, and that runs this function with these arguments. Thread yield basically relinquish the processor voluntarily. So you leave the processor voluntarily because you're waiting for IO or you're waiting for something. Thread join thread, that is basically the parent waiting for some of the forked threads to exit and then return. So if you are a parent, I mean, just when, like we were talking about process management in the previous few slides, if you are the parent, you can actually start new threads, and they're, well, you just use thread create, for example. And as a parent, you can wait for forked threads to exit, basically. So you wait until all your threads are done. You start child processes, child threads, sorry, and you wait for them to be done and before you do anything. And then there is thread exit, which basically is the call that thread calls to quit and clean up whatever memory it has been used and wake up any joiner. So if it had a parent, then it will wake up the parent. There is a thread API where you have basically asynchronous procedure calls. The caller continues execution and does not wait for